Okay, so we'll start on page 88. We are right now starting lesson 11, which is up here, solving systems by algebraic methods. So what we just did for the bulk of today's class was solve a system of equations. Remember, a system is just more than one equation. All right, so again, what we did for all of today's class was solves systems of equations graphically. So what that meant, remember, a system of equations is just more than one equation. For us, it's always going to be two equations. And when we're looking for a solution to the two equations, what we really mean is an x and a y that satisfies both equations. Graphically, what did we discover that really meant? Where they cross, okay? So solving a system of equations graphically just means find that point of intersection. But there's some problems with that. First and foremost, did you guys always get exactly the right answer? No, right? I mean, you were close and you might have been perfect on some of them, but as soon as you start plotting points, you are going to be estimating, right? And so your answers are going to be estimates. And, you know, I mean, they were close most of the time, but not perfect. Also, graphing lines takes a long time, right? And so we're going to come up with a way here that is better than graphical, in that it's always going to be perfect. And with practice, I think it goes a lot quicker than the graphical approach. So here we go. In this lesson, we solve systems algebraically, not graphically, which is what we did in our previous lesson, using two methods, substitution and elimination. So the kinds of equations that we're going to be solving are exactly the same as the ones that you just did. For example, there are two equations. If you use the technique from earlier today, you would find points, you would draw two lines, and you'd estimate the point of intersection, right? We're going to come up with that same answer, but without any graphing. So a completely different technique, but the goal is still the same. Okay, so the step-by-step solution is written out here, but I want us to actually like write it all out ourselves. So I think there's going to be enough room here at the bottom. Can somebody read to me those two equations, 6x? Any other? Okay. So can everybody just copy those two equations down here at the bottom? I think there's room. What's that? Oh, it is right there. It is right there. Yeah. Okay, so we're going to ignore, like I said, it's all written out there. I typed it all up, but I want us to actually just do it from scratch here. So let's give it a shot. The first technique is going to be called the substitution method. It will become clear why it's called that in just a couple of minutes. What we are going to do first is solve one of those two equations for one of those two letters. That means we've got four options. Solve the first equation for x, solve the first equation for y, solve the second equation for x, or solve the second equation for y. It turns out that in this case, one of those four options is much easier, much more friendly than the other ones. And we'll do the friendly one, and then we'll take a look at why that one's friendly. Did you have a guess there? Second equation for which letter? Okay, so Jeff has some insight here. He thinks that solving the second equation for y is the friendly one, and he's right. So let's do that. So solve this equation for y means move that 4x to the other side by subtracting. So we get y is equal to 5 minus 4x. Everybody good? If instead of solving that equation for y, we had chosen, don't copy this part, this is the unfriendly part, but if we had chosen to solve for x, okay, we can do it. First, you have to move the y to the other side. So we subtract the y. Remember, you're not copying the stuff here in blue. Yeah, but then solving for x means we got one more step here, and it's a division, which means there's fractions. 5 minus y, all divided by 4. So totally fine, but a lot less friendly than what we have. Why did Jeff gravitate towards the y in the second equation? So why did we pick that one? I don't think it's because it looks like y equals mx plus b. You can, but I don't think that's why that's the friendly one. Becca? It's by itself. The thing that made the 4x problematic is that 4. That's why we had to divide by 4 at the end. But that y has an invisible 1 in front of it. So that was the best choice. Okay, Next step, after you've solved one equation for one of the variables, is to substitute. Remember, this is called the substitution method. We're going to substitute that stuff in for y in the other equation. You're going to substitute into the other equation. So this equation right here becomes 6x minus 2, I'm going to leave a little space there, equals -3. So it's just copying that first equation, but I've left a blank space where I should have put a y. And what I'm going to put instead is 5 minus 4x. Because after all, y is exactly the same as 5 minus 4x. So it's okay for me to do that substitution, right? How many variables were in the first original equation? 2, right? How many in the second equation? Still 2. When we solve for y, how many? When we solve for y, how many variables in that equation? Still 2, x and y. In this new equation, 1. That's why it's better. Okay, so now we'll solve this. 6x minus, so we're distributing that, right? The 2 comes in, 10 minus 8x equals -3. Serena, not calculator active. Becca? Becca thinks I made a mistake. Everybody else just copied what I wrote and has accepted it. Oh, I made a mistake. Really common mistake. What did I forget to do? That negative, right? A negative comes through. -2 times -4x plus. Got to be really careful. Okay, so we combine the like terms. 14x minus 10 equals -3. I add the 10 to both sides. Add 10 here gives 7. And then we divide both sides by 14. 7/14 is fine, but we want to reduce our fractions always. 1/2. Okay, this is most of the credit for this problem, but it's not completely done. Remember, the system of equations wants to know how much is x and how much is y, not just how much is x. And so there's one optimal place to go for finding the y, and that's the equation where we have y equals. Now you can go to any equation that has x and y, but if you've got an equation that says y equals, you go there. So instead of x, what are we putting in? Putting in this 1/2 that we just calculated. So I'll do this one in red again. Y equals 5 minus 4 times 1/2 that we just calculated. 4 times 1/2 is 2. So we get y equals 3. So write your final solution either x equals 1/2, y equals 3, or you can write it as an ordered pair. 1/2, 3. Yeah. Any questions on that? Okay, if we wanted to check our work, so the nice thing about a lot of algebra problems is you can check. You might have made a mistake somewhere in the solution, like in the process, but you can check. If this 1/2, 3 is indeed the solution to these original 2 equations, what can we can plug them in, right? We can change the x to 1/2 and the y to 3 and see if the first equation is true. and separately see if the second equation is true. And if we did that right, they should both be true. Let's just do the bottom equation real quick. Imagine plugging in x equals a half. So we're doing 4 times a half. How much is half of 4? 2. All right, so this is a 2 plus, how much is the y? 3. 2 plus 3, 5. Worked. And if you plug in the first equation, that one will work too. The downside, like if you ended up getting like 2 plus 7 equals 5, so that means we made a mistake, but the downside is that this doesn't help us find the mistake. It just lets us know there's a mistake somewhere. We just have to go back and try to identify it. Okay, that right there was called the substitution method. Completely different technique here called the elimination method or the addition subtraction method. And it's based on a property that says equals added to equals are equal. So let's just see this real quick. If I wrote down 2 plus 5 equals 7, you'd say, you bet, right? No problem there. And if I said 6 minus 1 is 5, you'd say, hey, that's also true, right? Okay, so then if I decided I was going to add everything on the left-hand side, 2 plus 5 plus the 6 minus 1, just adding them all up, is that equal to adding them all up over here? 7 plus 5? It is, right? I mean, you don't even need to check the arithmetic. I mean, it was just 2 different ways to say 7 and 2 different ways to say 5, and so it's still 2 different ways to say 7 plus 5. Okay, so we're going to take advantage of that fact right here. So here's the system of equations we're going to solve. 9x plus 6y equals 5, and then 6x minus 5y equals 9. Thinking about the first step of the substitution method from the last page, solve one equation for either x or y. Are any of those 4 options there friendly? They're not, right? All 4 of our choices, solve the top one for x, solve the bottom one for x, all 4 of our choices would involve division and fractions, right? There's nothing wrong with it. You can like just do everything right, you'll get to the right answer, it's fine. But in a case like this, I personally don't do the substitution method because I'd rather not deal with all those fractions. I'm going to do this technique here. Okay, let us, what are we doing here? Okay, we're going to see if we can, again, the process is all written out there, but we're going to do it from scratch down here in number 2. Okay, I'm going to do something kind of strange here. I'm going to multiply that top equation by 2. You'll see why in just a minute. But if we multiply this equation by 2, what do we get? What do we get? 18x plus 12y equals 10. Really easy to forget to multiply the other side by 2. It doesn't stay 5. Everything gets multiplied by 2. Both sides times 2 is something legal. It's not clear why that's any better for us, but it's legal, right? It's another equation that's equivalent to the first one. And then I'm going to multiply this equation here, both sides of this equation by -3. So what do we get first? Negative 18x, and then plus 15y equals negative 27. So I've got 2 brand new equations equivalent to the 2 that we started with. But the nice thing here is that we have built this in such a way that if you add these 2 equations, what happens with this 18x and this negative 18x? They just cancel. And that's great. And how many y's do I have when I add the y's? 27y equals, and then we add these guys, negative 17. Super. That's it. Just like that, we've got our y. Just divide both sides by 27. Negative 17 over 27. Okay. Because I'm wicked smart.
Understood.
Yeah, that's exactly right. Nick is looking at exactly the right thing. Nick said we want something that both 9 and 6 go evenly into. What's the smallest number you can think of that 9 goes into and 6 goes into? 18 is the winner. They both go into 18. So in my mind, I said, okay, I'm just going to turn them both into 18x. What do I need to multiply this thing by to turn it into an 18x? Multiply by 2. That's where I came up with that. What do I need to multiply this guy by to turn into 18 is a 3. I chose to do -3 because I really like having opposite signs here. Right? And then they were both 18x or 1 plus and 1 minus, and then it's just bookkeeping, right? Okay, so that's great. Now, again, this is only part of the process. What else do we need to know? Still need to know the x. Okay, I have changed the way that I teach this now. For many years in my career, I would say, okay, y equals -17/27. Plug this thing in for the y in either equation, for example, right there. And so you can plug in y equals -17/27, and then that equation only has x in it, and you got to do some work to find x. But my goodness, is that messy. And then a couple of semesters ago, one of my students showed me the way, and she said, hey, why don't you just start the problem from scratch? We chose to eliminate the x's by making them both 18x. Why don't we just start over and eliminate the y's completely separately, because plugging -17/27 in is challenging. Let's give it a shot. Okay, I'm going to recopy my 2 equations. Why don't we just use them from up above? We've still got them up here. Okay, here are my 2 equations. The goal is to get rid of the y's. So don't say the answer to this out loud. But the question is, what can you turn, what does 6y go into and 5y go into? Okay, go ahead, say it out loud. That's fine. Fine. Right. 30 is the lowest common multiple of the 6 and the 5. So we're going to turn both of those guys into 30 y's, 1 plus and 1 minus. So the question is, what do we need to multiply this thing by to turn the 6y into a 30y? It's 5. So multiply everything in that equation by 5. So what do we get there? 45x. N equals 25. And we're trying to turn that -5y into a -30y. So what do we need to multiply it by? 6. In this case, I would keep it as a +6 because they already have different signs. And I like that they have different signs. Okay, so 6 times everything. So what do we get? 36x minus 30y equals 54. Great. And what wonderful thing happens when you add these 2 equations? The y's cancel because we built them to cancel, right? We turned them into the same thing but with opposite signs. And the reward is that the terms cancel. Okay, so we just have to add up the x's. How many x's? $81, right? So we got 81x. The y's all disappear, equals, and then we add on the right-hand side. 79 is good. Lo and behold, a really easy equation to solve, right? X equals 81 over 79 or 79 over 81? 79 over 81. That's it. And as your final step, as usual, write it as an ordered pair. Just put the 2 numbers near each other, right? Okay, so I'll come down here. So our solution is, we said 79 over 81, comma, what's the other one? -17 over 27. So again, that's called the addition subtraction method because you're just adding 2 equations together. You could subtract 2 equations. I typically always add. I make opposite signs so that I'm always adding. It's also called the elimination method because what happened when you added the 2 appropriate equations, one of the variables got eliminated. Okay, 2 different techniques. In terms of what you are responsible for, like on a test or a quest, remember, none of this is on the upcoming quest, but it will be on the first test. You should expect that, so we now have 3 different techniques for solving the same kind of problem. Like I could give you those 2 equations right there, and I could say solve it. And you could say, oh boy, I have three different options. I could graph and find the point of intersection, or we could do the substitution method like on the previous page, or we could do this elimination method like on this page. What you should expect is that on the test, I'm going to ask you to do three different methods. I'll probably give you three different sets of equations. I'm going to say solve this one graphically, solve this one with elimination, and solve this with substitution. So even though you have three techniques that all solve the same kinds of problems, you don't get to just pick your favorite and ignore the other two. I'm going to make sure that you know all three of these things. Okay, just a little theoretical stuff here. Number 4, usually two lines intersect at a single point. That means there's just one solution, that's the default. But there are two special cases that we looked at in our previous lesson. Two parallel lines, how many times did they intersect? None, so no solutions in that case. And two lines that are really the same line, how many times do they intersect? Infinitely many, right? So if you're looking at a picture, like if you create a graph of two lines, then it's going to be obvious to you, oh, they intersect once, or they're parallel, or hey, I drew the same line twice. But for the techniques from this lesson, we don't draw any pictures. And so we need another thing that's going to cue us in to the fact that we're in one of these special parallel or the same line cases. So that's what we need to discover here on the next page. Number 5, use substitution to solve each of these systems. Something strange will happen when you solve, and then we're going to make some conclusions after reading number 6. So let's give it a shot. Part A. So here are our two equations. We're going to do substitution. Remember, with substitution, the first step is to solve one equation for one letter. Good news for us is this is already done. For example, the first equation is already solved for y. Okay, so that's good. And then we're going to substitute that into the other equation. So we're just going to substitute right down here, and I'm going to change that y on the left-hand side to a 2x plus 1. So this is kind of bad form here, but I really want to be clear. As I write this, look, I'm just substituting. I'm just changing the y into 2x plus 1. Because after all, 2x plus 1 is exactly the same as y. Okay, and then I got x's on both sides, so let's bring them over to the same side. So what happens here when we subtract 2x from both sides? The 2x's disappear, right? Subtract 2x from both sides and they disappear. So we're left with what funny equation? 1 equals 3, right? So we're not exactly sure what to do with that, but we can't, like, the answer is not x equals 5 or x equals 17. It's just there's no x at all, just disappeared. Okay, we'll come back to that. In part B, y equals 2x plus 1, 6x minus 3y equals negative 3. Okay, we're going to do substitution again. We're going to solve one equation for one letter. One of the 4 choices, x or y, is the friendliest one. Which equation do you want to solve for which letter? Yeah, we're going to do substitution. Which equation is already solved for which letter? Y in the first equation. So clearly we're going to use that one. So we are going to substitute for that y right there. Substitute into the other equation. Okay, 6x minus 3 blank space equals negative 3. That blank space is where the y was supposed to be. What are we putting there in this case? 2x plus 1, because that's just another name for y in this problem. So that's our substitution step. And then we distribute here. What do we get? 6x minus 6x minus 3 equals negative 3, right? What happens on the left-hand side? 6x's cancel, and we're left with the equation negative 3 equals negative 3. Which is, okay, it's true. But again, we don't have like an x equals 7 kind of answer. All right, so here are 2 special cases. What just happened is that the x's all disappeared. We're expecting to be able to solve for x. And outside of our control, the x's all vanished. Number 6, when solving a system of equations, if the variables all disappear, like right up here, that's our clue that we're in one of the 2 special cases. One of these 2 things is 2 parallel lines that don't meet at all. The other one is two lines that are exactly the same and meet in infinitely many points, okay? Here we go. If you end up with a false statement such as 7 equals -2, then there are no solutions to the system. If you have something false, there are no solutions to the system. The system is called inconsistent. It doesn't have any solutions. Which picture is that? Parallel lines or the same line? No solutions. Parallel lines, no points of intersection, right? Again, we're not using my math lab, but so we can just ignore that note. Down here, if you end up with a true statement, such as 4 equals 4, then there are infinitely many solutions to the system. That's the same line twice. In that case, the system is called dependent. One line depends on the other line because after all, they are exactly the same line. Okay, let's go back up and make some conclusions up here. 1 equals 3. The choices are no solutions or infinitely many solutions. No solutions. Because we got some ridiculous equation that was obviously not true. 1 equals 3. And part B, -3 equals 3. What do we conclude? No solutions or infinitely many solutions? Infinitely many. And those are our conclusions. Serena. The fact that the x's disappeared means it's either none or infinitely many. Those are the only possibilities. If the x's disappear, then having one solution is not possible. Because if there were one solution, you'd have an equation that you could solve for x. You'd end up with x equals, 79 over 81 or something like that. So the x's disappear. That's supposed to trigger a little warning bell in our head. Hey, it's one of the two special cases. No solutions or infinitely many. Okay. All right, so we have 10 minutes left. Let's see if you can do this first question in those 10 minutes. All non-calculator problems. What you're going to do is write a system of equations for the given setup here. You're going to solve using substitution. Then you're going to solve again using elimination, and you're going to check. To be clear, even after you get the answer for x and y, you're going to solve again, completely from scratch. Once by substitution, once by elimination. Practice both methods on each of the on all the problems on this page.